committee, dear colleagues and guests. I'm glad to present you my work on real-time simulation of arm and hand dynamics using spiking neural networks. This work is advised by Sergey Yakovenko, and let's go through the structure of this presentation. First of all, we will discuss the motivation and research goal. I'll introduce you the problem statement. We will discuss the related works. After we will go through the proposed approach, we will discuss the evaluation metrics and objectives. We will go through the experiments results. And finally, we will discuss the conclusion and future work. So it's said to claim, but the demand of prosthetics is dramatically increasing. We believe that this work hold the potential for the future advances in prosthetic limb control, ultimately improving the efficiency and responsiveness of prosthetics during daily tasks, can significantly enhance the quality of life for amputees. Another field that can benefit from real-time simulation of arm and hand dynamics is hand interface for computer control or virtual reality. So previously, Mikhail Manukyan, in cooperation with Sergei Yakovenko and others, have shown that the inverse dynamic problem can be solved using artificial neural networks. They have shown real-time speeds with pretty low joint torques. And for this project, we will consider spiking neural networks to solve the inverse dynamic and, what's important, forward dynamic problems. We expect and want to verify that these networks will express directional tuning similar to their biological analogs. And also, such networks might be robust in the presence of sensory motor noise, and also such networks will be more computationally and energy efficient solution for the wearable devices integration. So let's discuss the problem first. The human arm and hand is pretty complex structure. If you try to analyze it, you will see a lot of joint and degrees of freedom. It depends on the model, but many researchers state of about 23 degrees of freedom and up to the 28 degrees of freedom for some musculoskeletal models. And to simulate arm and hand dynamics, there are two problems, forward dynamics and inverse dynamics. The inverse dynamics should predict the joint torques that should be applied to move arm and hand to the desired position, and forward dynamics should predict joint angles, velocities, and accelerations by the applied joint torques. On this slide, you can see the equations that generally describes the IDM and FDM that solves the respective problems. So let's discuss the related works. First of all, we reviewed the previous work made by Mikhail Manukyan. In this work, authors compares various artificial neural networks, such as recurrent neural network, gated recurrent unit, and log-short time memory. For the inverse dynamic problem, they have proved that these models are suitable for real-time application with low joint torques. But in this work, there are some limitations since it's based on data-driven approach. There is pretty limited exploration of behavioral space. This method can solve inverse dynamic for unseen behavior, such as object interactions or pathologies like tremor. Also, in the dataset they used, hand joints are not fully covered. So for most of the joint was represented in the dataset like constant zeros. And another field is robotic arm dynamics, which closely related to the human arm and hand dynamics. This work by Athanasios Polidoros and others proposed the online learning-based approach that includes adaptive learning rule to compensate some change in dynamics like for the object interaction task. In this work, the dynamic was considered by for the 6 degrees of freedom robotic arm, and also this approach is pretty computationally demanding because of reservoir layer. Another work we will discuss is the Travis de Wolf and other work on spiking neural networks for arm control. In this work, authors implemented neurally plausible architecture that includes premotor cortex, primary cortex, sensory cortexes, and of course cerebellum. In this work, authors also propose to use adaptive learning rule based on the inverse dynamic control signal to adapt to the changes in the hand dynamics. Unfortunately, this work doesn't discuss any real-time performance of the solution, and the implementation was limited only by 3 degrees of freedom. So let's move towards the proposed approach. We are about to employ the following advantage of the spiking neural network in our project. Such networks are energy efficient and might work on a special neuromorphic device such as Loihi. And these networks are also perfect for the temporal data processing, and of course, it's biologically plausible. But the training process of such networks is a bit complex process compared to the regular deep learning models. Also, some models of neurons can be computationally complex. We propose to use Nango in our simulation toolkit, and this software built on top of the neural engineering framework, which we will discuss a bit later. In this software supports Loihi and FPGA hardware, which allows us further integration with low energy wearable devices. For us as developers, the Nango also provides web-based simulation environment, so we can easily set up our experiments and visualize actually hand and arm state in real time. Is as a disadvantage is well known that Nango has scalability issues, so we would need to optimize the number of neurons of our model. So let's move to the neural engineering framework. It provides 3 main principles that allows to model and train the spiking neural network. By the representation principle, signals encoded in neural populations based on the tuning curve of each neuron. The spiking activity of neural population can be decoded to recover the original input signal or some transformation of that input signal. You can see the encoding simulation of the 8 neurons in the leftmost column of the plot in the top panel, and there are tuning curves of the neurons. In the middle panel represents the input signals, and the bottom panel represents the encoded spikes of that neurons. On the next column, you can see the decodings in action, moving from the encoded spikes in the top. It goes through the decaying exponential filter in the middle, and the filtered activity is then combined with the set of weights approximating the input signal, which you can see in the bottom panel, actually green line. By the transformation principle, populations of um, neurons can send signals to another population by decoding the desired function from the first population and then encoding the decoded estimate into the second population. On the next column, you can see sine wave encoded by a population A. On the top panel, it's projected as its negative on the population B in the middle panel, and its square is projected to the population C on the bottom panel. And by dynamic principle, signals being represented by population of neurons can be thought of as a state variable in the dynamical system. You can see the dynamical system which creates harmonic oscillator plotted over time on the top panel and its state space on the bottom panel. And the NANCO implements the stated NAF principles, so we can approximate functions from the problem statement using the decoded connections. In the right-hand side, you can see the scheme of such a connection. It allows us to set up decoded connections between ensembles of spiking neurons to implement the IDM or FDM. So let's discuss the evaluation metrics for this project. First of all, we propose the root mean squared error for the applied joint torques. Second metric stands for mean absolute error for the position of any effector in the task space. And finally, we will track the simulation latency to conclude about its real-time performance. And it's important to mention that the evaluation process was performed without rendering the graphical interface in the pure simulation mode to avoid overhead for latency measure. And to achieve the goals of the project, the proposed model must reliably predict joint angles and torques with minimal error. So for the inverse dynamic problem, the model should predict the joint torques with RMSE less or equal to zero point 0.1, and for the forward dynamic model, uh, uh, the the model should accurately predict the joint angles, so the overall model capability to accurately move the arm and hand to the desired position is expressed as MAE in task space should be less or equal to 5 centimeters. And the model must also operate in real time, so simulation latency with which expresses the time of full pass for both FDM and IDM parts of the model should be less than 1 millisecond for the corresponding time step. So we used the following plan to achieve the research goal. First of all, we implemented a simple 1 degrees of freedom kinematic model in terms of design of networks and development. It's pretty similar to the dynamic ones. So we could lay out the networks connection at this stage. Next, we increased the number of degrees of freedom up to 3. So we could show the possibility of usage such networks with larger models. And we implemented the dynamic models based on the Majoko physical engine. And finally, we have shown how to optimize the proposed models. So according to the plan, first thing we have done, we considered the inverse and forward kinematics equations. You can see what's the difference between them and dynamics ones. On this slide, basically, it's a simplification that doesn't account for gravitational and frictional force, as well as mass inertia and for the arm and hand model. So the implemented model scheme you can see on this slide. There is visualization of IDM model, which consists of inputs and outputs nodes that used to scale the input data, and neurons population, which should predict the joint torques. Also FDM model, which contains, again, inputs and outputs, nodes for scaling purposes, and also FDM ensemble to predict joint accelerations and store it to the node called DDQ, and corresponding ensemble to integrate joint velocities called DQ and angles Q. In the right top corner, you can see the visualization of the corresponding arm model. For the evaluation of all the presented experiments, we have used simulations of 25 seconds with randomly generated target trajectory. You can see that the proposed 1 degrees of freedom model has really low joint torques error as well as task space error. Also, latency is within the required real-time bounds. For the visualization purpose, we've used the simulation with predefined target trajectory. On the top part of the plot, you can see the desired and actual hand positions over time. The green and orange dashed line represents the desired position over X and Y axis, and blue and orange lines represent the actual positions respectively. The bottom part of the plot shows mean absolute error in the task space over time. As the next step, we implemented 3 degrees of freedom kinematics model. This model contains 3 joints, which are shoulder, elbow, and wrist, and 3 links, which are upper arm, forearm, and hand. So as you see, the proposed model has actually the same structure as the previous, but with 5 degrees of freedom. And as you see, there is pretty good metrics with the within the requirements bounds. So let's move to the bit more complex task, which is the dynamic model. So we used a Majoko physical engine to compute the forward dynamics, and it allowed us to use that outputs as ground truth data to feed our model and evaluate it. During the experiments, we found that a single population of neurons is not capable of predicting the joint torques of the dynamic model for the IDM part. So we had to split the original joint torques equation into 2 parts that allowed us to reduce the number of neurons and also the number of dimension for the corresponding neural populations. So you can see that the target metrics are a bit of the requirements. On the plots, you can see that the error started oscillating and the model wasn't quite stable. So we had to consider some extra optimization techniques. The NanGo-DL framework introduces the possibility to use regular deep learning techniques to optimize the spiky neural network even further. The main idea is to use differentiable approximation of spiky neural network, spiky neurons during training and employing that spiky neurons during and employing actual neurons during inference. Moreover, using this approach, we can optimize all networks parameters such as encoders, decoders, and biases, whereas neural engineering framework method optimize only decoders. So we selected a hybrid approach when the connection weights were selected using neural engineering framework, but neurons population biases gains and encoders optimized using the deep learning approach. For the training, we prepared dataset with 10,000 randomly generated simulation with 100 steps per simulation. For every simulation, we've randomly selected initial arm joint angles, position, and velocities, as well as desired target positions. We've used Adam optimizer with a learning rate of zero point 0.1, MSE loss for joint torques. We've configured learning rate decay by factor zero point 0.1 with patience 10 epochs and also early stopping with patience of 20 epochs. The training was performed on the RTX 2070 GPU with 8 GB of memory. It took about 6 hours. So in result, we got better performance compared to the previous results, and the task space error was much more stable over the simulations. So on this slide, you can see the overall table with all the experiments results. We must claim that all the evaluation simulation was performed on the MacBook M1 Pro with 8 CPU cores and 16 gigabytes of RAM. Also, we have executed similar simulation on Majoko for the 3 degrees of freedom model to compare its real-time performance. As you can see, it's much lower than ours. And to conclude our contribution for this work, we've designed custom experiments and evaluation setup, as well as spiky neural network models, which with further optimization, which includes dataset collection and training, we've shown that these models can be used to solve both IDM and FDM problems in real time with accurate predictions of arm and hand dynamics. And also we have integrated the proposed model with a Majoko physical engine and used it to evaluate our final results. It also shows the possibility to further integration of our network with other arm and hand models such as MATLAB Simulink 1. And as the feature work, we proposed the following points. We could implement the model with higher degrees of freedom to simulate more sophisticated arm and hand models. And the one of main advantages of spiky neural network is the energy efficiency. So we could explore it by implementing the proposed model on FPGA devices or use specifically neuromorphic hardware since it should use much less energy for the computation and the inference time must be much faster. Also, we could consider the adaptive learning rule, which was proposed in several of reviewed works. This actually will allow us to model and account the changes in the hand dynamics. So that's it. Thank you for attention. Looking forward to your questions.
Okay, so question is about three dimension of freedom,
Degrees of freedom.
degrees of freedom, and is it enough? Is it too small? And how your latency will behave if you will have more dimension
Yeah,
degrees of freedom?
I see a question. Thank you. So actually, in this work, our goal was to show that spiky neural networks actually can handle inverse dynamic and forward dynamics. And we plan to, as I said, for the future work, increase the number of degrees of freedom. And we believe that using neuromorphic devices such as interlohi could help to, uh, might be used to actually parallelize the computations and compute those problems on even more degrees of freedom.
But you have stated at the start of your work a very low latency, 1 millisecond, if I'm not mistaken.
Yeah, 1 millisecond. Um Actually, we wanted to check if actually it possible to compute it within such a latencies um, because uh, we had to compare it with other works and our such as Mikhail Manukan one, and yeah, our task at this point was to do it in real time at our hardware uh, and with the desired latency.
Okay, thank you. Mm. The real applications of these approaches should be on edge devices.
Yep.
So with even less compute power.
Well, it's
So
not actually less compute. Sorry for interrupt you. We believe that using neuromorphic devices, which are more designed to compute spiking neural networks, would allow us to compute those problems even with less energy and even faster inference time.
okay, thank you. And there is no comparison of your current results using spiking neural networks with previous ones. So
Yeah,
it would be
actually, okay. So we compared on this slide, we compared the speed of our work, our latency with the Majoko ones, which is state of the art. And yeah, on this slide, you can see that we have much larger latencies, but for the larger degrees of freedom, we expect that our solution would work better on the edge devices. Uh, and also regarding the comparison it to the, for instance, Manukan work, it's not actually possible because in his work he used 27 degrees of freedom model, and as I mentioned before, that model, uh, it, despite it uses 27 degrees of freedom, it actually have a lot of zero coefficients in the data set, and actually they presented some metrics, but we cannot compare it with our work, and also we had different simulations set up.
I'm curious about this SNN um, spiky neural networks design. It like do you have to kind of change the architecture if the number of inputs changes?
Yeah, so we thought about this, and we specifically designed the in our source code. We designed all the computations to to change, and we so our code's ready to changes, and yeah, we simply have a simple variable that selects the number of degrees of freedom. But if we will talk about fingers, the hand, actually the palm, obviously it will require extra work to handle the task for the actually the fingers, because here you can see that we in 2D space move the arm into desired position, and this point is actually our end effector, the wrist.
Okay, and maybe last question is So, could you please a little bit maybe explain? So first you define this SNN architecture,
Yep.
but then you use Nango DL. So is it so when you use that part of framework, is it still counts that this is a SNN or this is some augmented model? Like
Yeah, it's still SNN. We use the NangoDL only to compute the corresponding weights and parameters of the model. And under the hood, an NangoDL, it replaces actually the spiking neurons with a differentiable versions, which allows us to use it, treat it as actual deep learning model. But when it comes to inference, we switch it back to the actual spiking neurons, and we will run it as really spiking neural networks.
and maybe again so this time last question. Uh, so I'm curious about the other domains the spiky neural networks are used, and maybe they model different processes, but like can you maybe tell us a little bit more about other domains, are the usages, and what are the results there? Do they perform good or bad?
Well, as I know, spiking neural network using mostly in the medical domain. For instance, the related works of Sergei Yakovenko supervised. So he supervised also the works related to the hand dynamics and everything related to the dynamics of the human parts. Um, Also, I saw examples in the robotic field. It actively used because robotics also requires low energy solutions, and yep, it used on the some facilities with the robotic arms, uh, and also such solutions uh, with the adaptive learning rules provides like flexible arms, which allows use it with a human interaction. Basically, when arms are not set to their desired position by force, but it moves slowly and it affects any interactions, which allows to use it with human interaction in robotics, for instance.
Okay, thank you.
Um, so can you please elaborate why do you use SNNs instead of other uh, architectures of neural networks?
We expect that it's possible to move spiking neural networks on the low energy devices. For instance, on the previous defender who showed his work, he used cloud solution, but we expect to run it on the edge device. Um,
So
so
it's more. So the first motivation, major one, is for this energy efficiency and using on the edge devices.
yeah, exactly.
Okay, interesting. And um, again, back to comparison of your results because it's probably the biggest part for my understanding. We do not have any baseline or compare with.
So regarding the baseline, we actually used a Majoko physical engine, which was our state-of-the-art baseline and target.
Yes, but you show us only latency, but not errors.
Yeah, because we trained our model to predict the values based on the Majoko output. So
Oh, yes. So then it's not truly comparable.
yeah,
You're
exactly.
already biased to Majoko.
And
And what about non, let's say, how to say, non neural networks approach? Like, I don't know.
yeah, exactly. The Majoko is non-neural network approach, and actually, there is one problem. I have one slide to elaborate that. So as you see here, the inverse dynamic problem takes much less computational power to run, and forward dynamics is uh, takes much more time. And in our work, we wanted to implement the forward dynamics on the spiky neural network, so it won't be it won't take that much time to compute that problem.
So again, about comparison, the problem with Majoko is that it's cost efficient, non-efficient. It's
Yeah, in
expensive.
terms of energy, computational cost.
Okay, so okay, I see then the reason. Then can you get back to slide number 15? Yes, so why those numbers?
So the first number in very top, we selected it because of recommendation of our advisor and based on the previous work from Mihailo Manukyan, which had actually the same requirement as well as simulation latency requirement, which is predefined and should be less than 1 millisecond. And for the task space error, we took this exact value um, simply as uh, top bound just to understand how good or bad our model is. Um, so that's it.
And you constantly refer to work of Mihailo Manukyan, our alumnus. And do you compare? So, for instance, here you said that we want to have the same requirements, which is logical to compare with, but uh, do you have any comparison with the results of Mikhail?
Yep, actually, as I said before, it's not actually possible because we have different model, and also in our approach, we also consider forward dynamics, which wasn't implemented before.
Mikhail, okay, I see. Mhm. Can you get back to conclusions? Okay. Sorry. About this difference between kinematics and dynamics models. Can you explain the difference? Because I don't remember from my physics class.
At this step, at this very first step, we simplified the equation just to set up all the layout. And here the difference is that we excluded mass inertia and also error position term. So it's still
So for kinematics, you exclude
actually
inertia. Okay.
for the kinematics.
And in dynamics, it's more.
Much complicated form equation. So yeah, we considered it at further steps.
And the last one from my side, why the 3 degree of freedom again? Why not 4, 5,
Well,
23?
actually, if you take a look at the hand, it actually has a shoulder, uh, elbow, and wrist. And if you try to increase the degree of freedom, you will end up to touch the fingers. And at this point,
It's
if
too
we
complicated.
yeah, it gets really much more complicated.
So I mean that either you have 1, 2, 3 or 23 and no in between.
Well, yeah, like that, but we can actually start to increase it slowly, like use 1 degree of freedom per each finger, and so on, up to 23.
Okay, thank you.
And also uh, this work is presents 2D space problem, but we also can move into 3D space, which also increases degrees of freedom.
Okay, thank you, Andrei. Що, ну тоді зробимо перерву. Добре, в нас перерва до 15:40.